Welcome back to the deep dive. Today we are digging deep, quite literally, into the soil beneath our feet.
We are. We're talking about nitrogen.
Exactly. Nitrogen in the soil. It's this, well, invisible engine driving our global food system. And it's kind of a paradox, isn't it? Essential, but incredibly flighty.
It really is the great paradox. Nitrogen's fundamental. It's in all proteins, nucleic acids. Every living thing needs it.
Right.
But in the soil, it's the #1 limiting nutrient across the globe. And the stakes are, well, they're huge. Our sources show something like half the world's population depends on nitrogen fertilizer for their food.
Half the population. That's staggering.
It is. And we're using about, 132 million tons of fertilizer every year worldwide.
Okay, so that really sets up our mission today. We're looking at this system we absolutely depend on, but it hinges on an element that's inherently unstable. We've gathered sources covering the element itself, the cycle, this constant microbial churn, the different forms it takes, how it disappears, which sounds, frankly, terrifying,
It can be.
and how people actually try to manage it. So our goal is to give you a sort of rapid grasp of this invisible battle. Nitrogen is constantly fighting down there in the dirt.
Let's start with nitrogen just as an element. It's the first one in Group V on the periodic table, the nicogens.
Right.
And while we struggle to get enough usable N, the irony is the atmosphere is loaded with it. About 50,000 tons of nitrogen gas above every square foot of Earth.
Hold on, 50,000 tons per square foot just floating above us.
That's right.
So why isn't farming easier? Why aren't we just, I don't know, sucking it out of the air?
Well, because almost all of that atmospheric nitrogen is N2 gas, diatomic nitrogen.
Meaning
those two nitrogen atoms are triple bonded together. It's one of the strongest bonds in nature. It makes the gas incredibly inert, stable, basically unusable by most living things.
So it takes a huge amount of energy to break that bond, like lightning or...
Exactly. Lightning does it naturally. Or the Haber-Bosch process, the industrial method we use for fertilizer.
Yeah.
Massive heat and pressure. That's why it's not just freely available.
Okay, that makes sense. So the N that does make it into the soil, how much of that can a plant actually use? Because you hear about total nitrogen, but that's not the whole story, is it?
Not at all. That's the critical point. The vast majority, maybe up to 98% of the nitrogen in soil is tied up in organic matter. Think dead plants, microbes, residues, humus.
Locked away, unavailable.
Completely unavailable to plants directly. They need the inorganic forms. And that makes up only about maybe 2% of the total N in the soil at any given time.
Just 2%. That's the pool plants are drawing from. And this is where it gets really interesting, because that tiny fraction exists in two main forms, right?
Yeah.
They behave very differently.
Very differently. It all comes down to their electrical charge.
Okay.
First, you've got ammonium, NH4 plus favor. It has a positive charge.
Positive charge. Okay.
Now, soil particles, especially clay and organic matter, they tend to have negative charges on their surfaces.
Opposites attract.
Exactly. So the positively charged ammonium sticks to the negatively charged soil particles. It gets held or fixed. This makes ammonium less mobile. It doesn't wash away easily. It's the more stable kind of banked form of usable N.
Okay. The sticky nitrogen. What's the other one?
The other one is nitrate, NO3.
Right.
And this one is the polar opposite. It carries a negative charge.
So it repels the soil particles.
Right. Like charges repel. It doesn't stick. Plus, it's highly soluble in water. Dissolves very easily.
Uh-oh.
It was right. That makes nitrate extremely mobile, extremely unstable in the soil environment. It's prone to washing out, leaching. It's the runaway nitrogen.
Stability versus mobility. The sticky versus the runaway. And managing that balance, that constant shifting between NH4 plus and NO3, that's key. So what drives that shift?
Microbes. It's almost entirely driven by microorganisms in the soil. This is the heart of the nitrogen cycle.
Microbial engine.
Absolutely.
Yeah.
And we need to look at, let's say, 3 core processes these microbes carry out that dictate nitrogen's fate. Is it being released? Is it being locked up again? Or is it being converted to that risky nitrate form?
Okay, let's start with the release. Making that big 98% organic pool available, that's mineralization, right?
Correct. Mineralization. This is where microbes decompose organic matter, dead stuff, manure, residues, and they break down the complex organic N compounds.
And they release.
They release it as inorganic ammonium, NH4 plus fade. That specific step, the release of ammonium from organic compounds, is called ammonification. The microbes are essentially unlocking the stored N, turning it into plant food.
Okay, so the microbes are helping out there,
Mhm.
but they can also work against the plants, right? There's the opposite process, immobilization.
Exactly the opposite. Immobilization is when the microbes themselves gobble up the available inorganic nitrogen, ammonium or nitrate, and use it to build their own bodies, their own
They
biomass.
steal it.
In a way, yes, they need nitrogen too, just like plants.
Yeah.
This happens especially when microbes get a sudden feast of high-carbon material, but that material doesn't have much nitrogen in it.
You mentioned the CN ratio, the carbon to nitrogen ratio.
Right. If you add something with a wide CN ratio, say over 30 parts carbon to 1 part nitrogen, like
Mm.
straw, sawdust, wood chips.
Lots of carbon, not much nitrogen.
Exactly. The microbes have tons of carbon food, but they need nitrogen to metabolize it, to build proteins. So they suck up any available ammonium or nitrate from the soil water to balance their diet.
And that leaves less for the plants, creating a temporary shortage.
A very real, temporary N deficiency for the crop. The microbes lock the N up in their own bodies.
Mm.
Now, eventually they die and decompose, releasing it again through mineralization, but in the short term, it causes competition.
Okay, so we have unlocking mineralization and locking up immobilization. What's the third big one? You said it converts the stable ammonium to the unstable nitrate.
Yes, and this is arguably the most critical transformation from a management and loss perspective. Nitrification. This is the process that turns the relatively stable, sticky ammonium, NH4+, into that mobile runaway nitrate, NO3.
Sounds risky. Is it one step?
No, it's a crucial two-step process,
Mm-hmm.
a kind of microbial relay race carried out by very specific bacteria.
Okay.
First, one group, typically bacteria like Nitrosomonas, takes ammonium, NH4+, and oxidizes it to nitrite, NO2. Now, nitrite itself is actually toxic to most plants.
Not good.
Not good. But fortunately, another group of bacteria, like Nitrobacter, jumps in almost immediately and oxidizes that nitrite NO2 further into nitrate NO3.
So ammonium to nitrite, then nitrate to nitrate, and this whole relay race, it needs specific conditions, right? It doesn't just happen anywhere, anytime.
That's a key point. Nitrification is quite sensitive. It absolutely requires oxygen. It's an aerobic process.
Mm-hmm.
So it happens best in well-aerated soils.
Not waterlogged soils.
Definitely not. It also has optimal conditions for temperature, usually best between, say, 25 and 40 degrees Celsius, roughly 77 to 104 Fahrenheit. And it prefers a soil pH that's slightly acidic to neutral, maybe 6.5 to 7.0.
So if soil's too cold or too wet or too acidic.
The whole process slows down or even stops. The nitrifying bacteria aren't happy, and the ammonium tends to stick around as ammonium, which is generally less likely to be lost.
Fascinating. But when conditions are right, this conversion to nitrate happens, and that sets the stage for potential problems.
Big problems. This constant microbial activity, especially nitrification, creates this volatile situation, and the consequence is nitrogen loss. It's a massive issue, economically for farmers, environmentally for everyone.
Yeah, you mentioned that figure earlier. Sources say up to 50% of the nitrogen fertilizer we apply can just disappear before the plant uses it.
Up to 50%, yes. That's a stark number.
Yeah.
That inefficiency, that loss, is driven mainly by three major escape routes.
Okay, let's break those down. The first one seems obvious given what we just discussed about nitrate. Leaching.
Exactly. Leaching is primarily the loss of nitrate, NO3, because it's negatively charged, doesn't stick to soil, and is super soluble in water.
Any extra water just flushes it down.
Flushes it right down through the soil profile below the reach of plant roots. If it gets into groundwater or drainage water, it's lost to that field and can cause environmental issues downstream.
And how bad can leaching be?
It varies hugely with soil type, rainfall, irrigation.
Yeah.
But in some conditions, like very sandy soils or soils like laterite mentioned in some sources, losses can reportedly be as high as 60%.
60%. Wow. Okay, what's the second escape route? Denitrification. Sounds like unnitrifying.
That's exactly what it is. Denitrification is the process where nitrate, NO3, is converted back into nitrogen gases, mainly inert N2 gas, but also nitrous oxide, N2O, which is a potent greenhouse gas.
So it goes back to the atmosphere, where we started.
Pretty much. It completes the cycle in a way, but it's a loss from the soil system. This happens specifically under anaerobic conditions.
Meaning low oxygen, like waterlogged soils again.
Precisely. When soil gets saturated with water, oxygen levels plummet. Certain microbes, needing something to breathe electronically, use nitrate instead of oxygen. They chemically reduce the nitrate, step by step, back into gaseous forms.
And the losses from that.
Can be really significant. Depending on how long the soil stays saturated, denitrification can account for losses of, say, 10% to maybe even 40% of the applied nitrogen.
Okay, so we have leaching, washing it down, denitrification, sending it up as gas. What's the third one? Ammonia volatilization, evaporation.
Basically, yes. Nitrogen escaping as ammonia gas, NH3, directly from the soil surface into the air.
How does that happen?
This is a major issue, particularly with certain fertilizers like urea, especially when they're just broadcast on the soil surface and not mixed in.
Why urea specifically?
When urea breaks down in the soil via enzymes, one of the intermediate steps produces ammonium, NH4+. But this breakdown process also temporarily increases the pH right around the fertilizer granule.
Makes it more alkaline.
Right. And in alkaline conditions, high pH, the chemical equilibrium shifts. More the ammonium, NH4+, converts into dissolved ammonia gas, NH3. If this happens at the soil surface, that ammonia gas just, poof, volatilizes into the atmosphere.
Especially on high pH soils to begin with, I imagine.
Absolutely. And warm, windy conditions make it worse. That's why getting urea incorporated into the soil quickly or using treated ureas is so important to minimize this loss pathway.
Man, it feels like nitrogen is just trying to escape constantly. Down, up, or just evaporating off the top.
It highlights the challenge.
Yeah.
But management can make a difference. We talked about immobilization with high carbon stuff.
Right, like straw.
Well, the flip side is using things like green manures, cover crops that are tilled in. They often have a narrow CN ratio, maybe 1.5 to 1.7 parts nitrogen per 10 parts carbon.
Lots of nitrogen relative to carbon.
Exactly. So when microbes decompose that material, there's plenty of N. It speeds up mineralization and avoids that temporary N lockup or immobilization problem.
And what about adding N naturally? We can't forget the legumes.
Definitely not. Biological nitrogen fixation, BNF. That's nature's way of getting that atmospheric N2 into the system. Microbes like rhizobia form partnerships with legume plants' roots.
Like peas, beans, clover.
Right. And they have special enzymes to break that super strong N2 triple bond and convert atmospheric nitrogen into ammonia, which the plant can then use. It's a huge natural input. Some sources mention cow pee fixing around 90 kilograms of N per hectare per year. That's substantial.
90 kilos per hectare. That's like several bags of fertilizer just made naturally.
It's a powerful process. It reduces the need for synthetic inputs.
Okay, so let's try to wrap this up. What does all this mean for, someone listening? What's the big takeaway?
I think the big takeaway is that soil health and fundamentally our ability to feed ourselves hinges on managing this incredibly small, dynamic 2% fraction of inorganic nitrogen.
This tiny pool of ammonium and nitrate?
Exactly. It's subject to cost microbial transformations being unlocked, locked up again, converted, and all these major loss pathways constantly threatening to deplete it.
So the farmer or the land manager, they're kind of like an air traffic controller, trying to keep the ammonium stable, trying to make sure the nitrate gets used before it disappears.
That's a great analogy. A very nervous air traffic controller. Because the system is inherently leaky, our sources really emphasize that even with careful management, significant amounts of N are often lost. Understanding these pathways helps explain why timing, placement, and the form of N applied are so critical.
It really drives home the complexity. We've seen how fast N can change forms, how easily nitrate can be lost from the root zone. Which leaves me with a final question for you, the listener, to think about.
Okay.
If nitrogen is so vital for plant growth, but that nitrate form plants readily use is so prone to disappearing from the soil, how does a plant cope if there's a sudden nitrogen shortage during a critical growth spurt? What's its backup plan?
That's a fantastic question to ponder. And the clue lies in observing the plant itself. Think about this. Nitrogen is actually mobile within the plant.
It can move around inside the plant?
Yes. So when a plant starts running low on nitrogen from the soil, where do the deficiency symptoms going up? The yellowing, the chlorosis usually show up first.
I think. Is it the older leaves?
Exactly. It's the older, lower leaves, not the new growth points. That's because the plant is smart. It scavenges the nitrogen from its older, less important tissues and redirects it, moves it internally to support the new, actively growing leaves and buds.
So it recycles its own nitrogen.
It recycles internally. It's a crucial survival strategy, a way the plant fights back against that very soil volatility and the constant threat of nutrient loss we've just spent this whole deep dive exploring.
A fascinating final thought. The plant's own internal management system mirroring the external challenge. Thanks for breaking that down for us.
My pleasure. It's
Wow.
a critical cycle to understand.